Second day of our odyssey through Math 120, contemporary mathematics. So again, it works a lot better if y'all got specific questions that I can answer. Otherwise, I'll just kind of head along the beaten path. But I know you'll will have more questions next week, because once the fire gets turned up on testing time, that's when people will want questions. But it really works better for a class if we do a little bit each time, and then I have a few minutes at the beginning of each class to answer questions. But I'll take them anytime during class, so don't be afraid to ask. All right. Let's see. Okay, our next stop on the Math 120 bus is for subsets, is what the particular topic is called, or the particular section. Now, I've got in my notes here, I got definitions, and especially as I get a little bit further in the course, I have nice graphics and stuff. But the subset is defined as all elements of the first set being contained in the second set. Now, since math people like to use symbols and such and use variables and such, so we got A and B. So if A, or all the elements in A, also exist in set B, then we write it like this. A, and this little symbol right here reads is a subset.
I don't see your screen.
It's not sharing? I'm seeing it on my.
I can see it.
Refresh your session. Like if you go in your browser and click the little refresh button in Google, it's up at the top, way top left, that little circle thing next to the house in the Chrome browser. And if you click that, everything will refresh. So if you're having any kind of issues like that and it's not rendering properly, that should fix it. Otherwise, if that doesn't work, then you got to get out and come back in the session.
Okay, yeah, it worked.
Okay, good. Okay. So a subset, I was gonna do. So this right here, I was just gonna put the symbol. Oops. That's not what I want. So I'm just gonna write it right here. That little symbol is not the easiest to render. So that's a very crude representation of it. It's the same thing that's right here. It's like I kicked over U with a line underneath it. And just like an inequality, that line underneath it means that equality is possible. And I'll show you what I'm talking about. All right. So this right here means is a subset. Okay. So let's go back up here. We got a set A that's got 2, 4, and 6 in it. And set B has got 1, 2, 3, 4, 5, and 6. Now, hopefully you'll notice that 2 is here and it's also in here. So this 2 is in there. 4 is also in B and 6 is also in B. Because all of A, it has to be all of A, is inside of B, then we can say that A is a subset of B. Okay? A is a subset of B. So that's what that term means. Think about it a second. Let me know if you got any questions.
What?
All right. So let's go on down. All right. Oh, that's fine. Let's talk about the C too.
Somewhere turn this
So we
on.
got this C, and it's the exact same set as A, actually. So those two sets are both equal and equivalent. A and C are equal and equivalent. And because they are equal, then we can still use the subset symbol, because underneath, you got that little line. See that little line right there? That means that it's can be equal and still be a subset. So therefore, we can say that A is a subset of B because C has 2, 4, and 6 in it, just like A does. And because they're equal, we can swap them around. That C is also a subset of A. Okay? Does that make sense? So when they're equal, you can do it both ways. With the regular, if it's not equal, but all these elements are in B, then you can only write it one way. A is a subset of B. It doesn't work the other way. But if the two sets are equal, you can put it either way, and it works. Now, closely related to that is proper subset. Now, the proper subset symbol is that one there. So that just reads well, what does that mean by proper? Well, a proper subset just means that everything in the set on the left is fully contained within B, but they are not equal. Okay? So what we were looking at up here with A and B, we could say that A is a subset of B, or we could say A is a proper subset of B. But C and A are not proper subsets of one another. They're regular subsets, but because it concludes the equal sign, we can use that symbol. But this one doesn't include this equal sign. So that means if it has equality, then it's not a proper subset. And what it amounts to is what we say here in part 2. Obviously, it's a subset, but part 2, it's got to be at least one element in B that's not in A. Okay? So as I had said up earlier, if A is equal to 0 and 1, and B is the same subset, then we can say they're regular subsets of one another, the subsets of one another, and even the other way around, that B is a subset of A, and they're equal. But A is not a proper subset of B, because a proper subset does not include equality. And I'll just put this as a note. Okay, so that's really the difference. You can also look at it like this, that there's at least one element. It doesn't have to be just one. It could be 2, 3, any number. It's just that they cannot be equal. Okay? Makes sense? All right, let's look at another scenario. So let B, C be 0, 1, and 2, and we're still using the same A Okay, so A so I was trying to find a way to get those where we can see them. There we go. I don't want to take the note off yet. So A is 0 and 1, B is 0 and 1. We already talked about since they're equal, they're subsets one another, but they're not proper subsets. So in this scenario, if we got a third one, C, which has got an extra one in there, that's the one that's different. Then A is contained within C. See? 0 is in there, and the 1 is in there. And that extra 2 is what makes it a proper subset, because both of these are inside of this set, but there's that one that stops it from being equal. So therefore, we can use this symbol for the relationship between A and C. A is a proper subset of C. And C is not a proper subset of A, nor is it a regular subset, by the way. Because if a set is larger, then it cannot be a subset of a smaller set, essentially, is what that means. All right. So that's how the subsets work, okay? You just got to make sure that everything in the one on the left is actually in here to the one on the right. If it's a proper subset, there's got to be at least one different. There's got to be like one less in the A in order for it to be a proper subset.
You call your mom?
All right, so let's talk about the number of distinct subsets. So if we got a set and we want to know how many subsets it has, then there's a little formula for it. The number of distinct subsets of any finite set A is given by this little formula right here. This is about as in the first half of the course, this is about as mathematical as this gets, because that's what we call an exponent. The 2 is the base, and the n is the power. Do y'all remember what that n does to that 2? What does that n do to the 2? Let me write this out then. So 2 to the n two is the base, and n is the exponent or power. So I'll show you in a minute. I got a little chart in around, but basically what that means is, depending on how many elements are in a set, and remember that's what n is, it's the count of elements in the set, then that's going to provide the number, once you take it and multiply it out, the number of subsets possible. So let's look at an example. The number of, okay, so if you got a set A that's got 3 elements in it, set A's got 3 elements, and set B has got 6 elements. Okay. So for subsets, two to the third power. Now, get used to using a calculator if you're not good at exponents, and not trying to be little people or anything, but this is important to get this right, because people will look at that and they say, well, that's 6. But you got to remember what that means. And if you don't remember, then you can use a calculator. And watch this. See this little thing here on this one? I wish I could show you the calculator on the TI. Let's see if I'll show you how to do it here, and then we'll go over to the TI, and I'll kind of show you. I don't have a virtual TI to show you is the problem. But anyway, we're going to take 2, put in that base. We're going to hit this button here. It says y to the x, and that says we're going to put 3. So that's the shorthand way of doing it, but they do it on calculators and computers and such. So that's 8. So there are 8 subsets. All right. It's always a factor of 2. Every time you add another element, it doubles the amount.
Does 2 represent the 2 subsets?
No, the 2 is just it's the base. Let me see if I can kind of explain this to you, and then I'll come back to this. But I'll see this element. This set right here has 0. This one has 1. This one has 2, and this has 3. So if we list all the subsets out, well, on an empty set, there's only one subset. That's the subset itself, the empty set itself. So there's only one. So 2, and you can see it down here, 2 to the 0 power, in other words, there's 0 elements, is 1. We keep using the 2. The 2 has nothing to do with the number of elements in it. It's just part of the formula, because every time you add another element, you double the amount. So watch here, 0. If we have 1 element, it's 2 to the first power, which is 2. Okay, 2. There's your 2 subsets, the set itself and the empty set. And then if we bring 2 elements in, A and B is 2. 2 to the second power is 2 times 2, which is 4. 1, 2, 3, 4. And what's going to happen again? See, it doubles it. And you can see here on the pattern here to the right, 1 doubled is 2, 2 doubled is 4, 4 doubled is 8. If we do further than that, 16, 32, 64, 128, 246, I believe it is. And it just 256, and it just keeps going as powers of 2. So that's where that 2 comes from. It's part of the formula. It doesn't have anything to do with the number of elements in the set. The number of elements in the set is where the variable is at the end, and that's where you put this value at here. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And every time you increase that exponent, it doubles it. All right. So this one was 8. All right. Now we're let's go down here and do this one, and then we'll come back and do the prop. Oh, this is both of these are subsets. So now over here, so A had 3 elements, B has 6 elements. So for this one, for B, 2 to the 6th power. All right, so let's look at that calculator again. 2, hit that, 64. All right, so 64 subsets that could possibly exist given this set. And what it amounts to is we could take out the 1, we could take out the 2, we could take out the 3, we could take out the 4, we could take out the 5, and take out the 6. Each one of those 6 would be subsets. Then we could go in and do them 2 at a time, 1 and 2, 1 and 3, 1 and 5, 1 and 6, and so forth. But there's going to be 64 of them. And that 64 includes the set itself, because we're asking about regular subsets and not proper subsets, and then also the empty set. I'll go over that in a little bit more detail in a bit when we get back to that chart. Now, right here is where proper subsets. Here was just subsets. Here's proper. Well, if you remember back up there when we were talking about proper subsets, I had mentioned that proper subsets cannot have equality. What we do is we throw out that one that's equal 1, which is where this formula comes from. So when we find out the number of proper subsets, we subtract 1 from the total to get how many proper subsets. The one we're subtracting is the one that's equal. Because when we go from subsets to proper subsets, we take out the one that's equal. So for this, it would be 8 minus 1 is equal to 7. And then 64 minus 1 is equal to 63. Okay, so there are 7 proper subsets and 7 proper subsets for A, for this one, and 63 for this one. All right, so let's go down. Oh, and this is an important thing I need to tell you before we go back to that little chart thing. The null set is a subset of every set. All right, because you can always take out nothing. You can always take out the set that does not have anything in it, and that's considered a subset. So the null set is a subset of every set. All right. So here's 4 different sets, and I'm going to go through this in a little bit more detail. All right. So if a set is empty, like this set here, an empty set, there's 0 elements in it. That's the definition of an empty set. And that was one of the things that I wanted to make sure we understood. So in the morning session, I had spent the last few minutes talking about what an empty set is. It's just a set that doesn't have anything in it, not anything complicated. So there's 0 elements in that set because there's nothing in there. So 2 to the 0 power, and people will have a hard time wrapping their head around that, because how can that be? Well, 2 to the 0 power is 1. And you know why? Because it doesn't matter what the base is. Anything to the 0 power is 1. If we have we have negative, oh, I still get that 0 there. All right, let me focus. I'm going to put a real big number in there. And I'm going to raise it to the 0 power. And see, that's 1. Anything, any value to the 0 power is 1. I don't know why it didn't, had that 0 in there, but that's still negative 4,500. So positive, negative, anything to the 0 power is 1. So that's why there is only one subset. And because of the fact that the null subset, the null set is a subset of every set, then there is your subset right there. That's listing it out. When they're small, we can list them out. If you got like more than 8, which is why I stop here, you get a lot of them. We're not going to get too much into that. So there's your one distinct subset. And it's actually the same set, which is fine as a subset. But let me put over here another little thing so I can so in there, I'm going to put the number of proper subsets because this chart doesn't have it. So I want to add it just to kind of give us a little exercise here. And just remember, all we're doing is we're using this formula here to subtract out 1 from the column directly to the left. So 1 minus 1 means we have 0 proper subsets for an empty set. And that kind of makes sense because the empty set and the empty set are equal, so it's not a proper subset. So there are no proper subsets for an empty set. All right, so with one set, one element in the set, 2 to the first power, 2 to the first power is 1. I'm sorry, 2 to the first power is 2. And you can see the word down there when I scroll down. I was just trying to have this there in order to see why that went away. All right, so on this one, the set that's exactly like it, the A is not a proper subset, so that's why we subtract out 1. So here we would have just 1 left after we subtract out 1. All right, so on this one, 2 to the second power is 4. And so we're going to take out the one that's just like it. So in this case, it's going to be 3. And this is like the one that I answered earlier. There's 8 distinct subsets. So we would throw out one of them. And in this case, it would be that one, the top one, the one that's exactly like the set there to the left. So this is all right. So there we got how subsets work. Okay, the number of subsets. So the number of subsets can be just calculated using the formula 2 to the n. And that was what was done down here. And I'll just point that out one more time. 2 to the 0 power. This is your power. The 2 is the base. 2 to the 0 power is 1. So 1 subset, subtracting 1 gives us 0 proper subsets. 2 to the first power, the number of elements is 2. So there's our 2 distinct subsets. Subtract 1 to get proper subsets. If we got 2 elements, that's 2 to the second power right here, which is 4. So 4 subsets. Subtracting 1 gives us 3 proper subsets. And 2 to the third power is 8. So 8 subsets and 7 proper subsets after we subtract 1. All right. Hold on a second. Let me look at something here. All right. I want to the way that it works in the Newton is they kind of cover complements. So I'm going to go up here and look at complements, and then I'll kind of start at the beginning. And then I'll come back and start from the beginning on that. Let's see. Where do I first look at complements? I want to go over complements because some of those questions you have are going to talk about complements. And somewhere in here, oh, I must have passed it up. Okay, here we go. All right. All right. The complement of a set. The complement of a set is the set of all elements in the universal set that are not in A and denoted A prime. Or that little thing right there at the top up there. That little thing right there. That just means A complement. So you read it as A complement or A prime. But what a complement of a set is in the original set, or if you put it back together, you get your original universal set. Well, what do I mean? Well, look at this. Let's let U, the universal set, be the natural numbers 1 through 10. Okay, 1 through 10. Now, A is going to be 2, 4, 6, and 8. So 2, 4, 6, and 8 are being pulled out from U. All right, we're just an arbitrary set, 2, 4, 6, and 8. All right, and you see all of those are in U. Now the complement of A, are all the ones that are not 2, 4, 6, and 8. So if we take out 2, 4, 6, and 8, what's left is 1, 3, 5, 7, 9, and 10. Okay. And then you can see that they have nothing in common because they're complements of one another. That's what the word complement means in regards to the set theory here. It means that they are opposites of one another, essentially. Okay, that's what complement means. So when you see that little thing up there, yeah, and they use the same symbol. I was just trying to double check that they use that same symbol in the Newton. They do. Sometimes, like in our statistics course, they'll do it like this. Like A to the C for C being complement, but we don't have to worry about that here. So that one thing I wanted to cover here before I go back is the idea of a complement. So does everybody understand that, or any questions about that? Complement. All right, so let's go back up here. All right, so a Venn diagram is a way to represent two sets, where you can use three sets, and they even actually have a more with more, but you have to have computers to do that because it's not so easy to give an image of it. But this right here is what we call a Venn diagram. A Venn diagram is just that rectangular or square box, and it shows the relationship of some sets in there. We're talking about here in 2.3, for the most part, we're talking about two sets. So that's what this represents. The square represents the universal set, and everything inside of the rectangle and even inside of the circles are part of the universal set. The sets inside, or the circles inside, represent A and B. Now, what this right here gives us 4 different categories of how sets can be aligned with one another. The first is here is what we call disjoint sets. Disjoint sets have nothing in common. All right. So set A does not overlap with set B. So therefore, these sets are disjoint. They have nothing in common. So here's an example. If we if we have set A is 1, 2, 3, and set B is 5, 7, 9, there's nothing in common in there. So they're what we call disjoint. We could do the same thing with two infinite sets and show the relationship. If C is 1, 3, 5, and 7, and dot, 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 all odd natural numbers, and D is the even natural numbers, 2, 4, 6, and 8, those, they don't overlap. They kind of mesh together, sort of like this. All right. And a matter of fact, the complement set and its complement are going to be disjoint. They won't have anything in common. So here's the representation of that visually. If we just have set A is 1, 2, 3, and set B is 5, 7, and 9, you can see that there's nothing in common. That's why they're overlap. If there were some common number in, they would be overlapped, and then you would have it in the middle. And I'll show you in a second how that works. All right. If two sets are proper, if we want to have a Venn diagram that shows the relationship of proper subsets, then this is the way it would look. Okay, proper subsets. A is fully contained within B, fully contained within B. And I'll try to fill this in for you. Since A has 3, 5, and 7, all right. And now B has the other ones. 1, 2, 4, 6, 8, 9, and then I'll have to put 10 up here. Okay, so here's between, okay, the whole universal set. We don't know what's out here because we don't know what's in the universe, but B contains 1 through 10. Since A is fully contained within B, then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So true to what we've got written here about B containing 1 through 10 and A having 3, 5, and 7, we've established a Venn diagram that faithfully depicts that relationship, that A is fully contained within B. A is a proper subset of B. We didn't need to put the 3, 5, and the 7 out here again, because by putting them in A, they are also in B. Okay. All right. Any questions? I'm trying not to go too fast, but I'll go about probably get 2 more minutes, and then I'm going to make sure of a few things before we head out. All right. And if 2 sets are equal sets, then the only way you can really establish them visually in a Venn diagram is just to make one circle and show that that's both A and B. They're the exact same elements. Now, to show that, I'm stating that if A has 3, 4, 5, 6, 7, and 8 in it, all right, 3, 5, 6, 7, and 8. And B, well, it has a different looking thing, but you know what? That's the set builder notation. So this is the way that we would represent 3, 4, 5, 6, 7, and 8 through an inequality. Notice that I don't have any equal sign, but if I wanted to, I could do this and get the exact same one, X and that number. So just that, and then I'm gonna go 3, and then I'm gonna come in and I'm gonna write a little line right underneath to show equality. So this is another way that we could represent B using the set builder notation. So get used to the fact that sometimes there will be equal signs down here and sometimes not. So you got to catch on that when there's no equal sign, then it does not include this endpoint. Over here, there's no equal sign, so it doesn't include the endpoint at 9. That means it starts at the very next one on either side, which is 3 and 8. Because when you have a 3-part inequality, whether it's like this or like this, that means that X is between 3 and 8, and the equal means it's inclusive. Down here, it means X is between 2 and 9 inclusive, but it does not include the endpoints. So by definition, or by default, that means it goes in one more on either side. So when they're equal sets, as we said earlier, A is a subset of B, and B is a subset of A. When they're equal, you can turn them around and it still works. All right, lastly, overlapping sets, which is when they have some common elements. All right, common elements. Overlapping cell elements. All right, so let's try to draw these in here. All right, so everything in the whole circle, now this time we're given the universal set is 1 through 15. So what I'm going to do is I'm going to start in the middle with anything that's common, and they're telling us what the common elements are. And then I'm going to write them in where they go. So 7, 8, 9, and 10 go there because they belong to both A and B. When you're in that middle football shape of two circles in a Venn diagram, and when you got 3, we'll look at that eventually, you can also have 3. Whatever the section is that contains, that's inside of both, that's your common elements. Now I can work my way out over here. Let's say on A, what do I have? I got 1, 2, 3, 4, 5, 6. It's 1 through 10. But here's the thing is, you got to watch. I'm stopping at 6 because there's my 7. That's already inside of A right there. 7, 8, 9, 10. So now inside of A, I've got 1 through 10. 1 through 10. On this side, the ones that are not there need to go in. Okay. So have I got all the numbers that are in the universal set? Well, this one goes past 13, the universal set. So that means that there is a 14 that has not been used inside, but it's in the universal set. And a 15. Okay, so now look, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 elements in the set and all in their proper place based upon what we're told here. Common elements in the middle, and then 1 through 10 in A, and then 7, 8, 9, 10, 11, 12, or 7 through 13 inside of B, and then 14 and 15 are not in either A or B, but are in the universal set. All right, so take a few more minutes here and talk about these concepts. First of all, it's the intersection. The intersection of a set A and B are the common elements. And in other words, this right here was the intersection. This was the intersection of these two sets, the common elements. The way that we represent that is with this little crazy symbol. Okay. So this right up here would have been A intersection B. So let's look at an example. We've got a set A that's got 1, 2, 3, 4, 5, 6 in it. We've got a set B that's got 0, 2, 4, and 6 in it. And then 2, 4, 6 are the ones that are in both of them, highlighted in blue. So A intersection B is 2, 4, and 6. Now, that little symbol, there's going to be another one that's very similar to it. And then, of course, it looks very similar to the subset symbol. Well, the subset symbol is the one that's kicked over on its side. This one is like on its head kind of thing. If you want to try to memorize it within the concept of that it's like an eye for intersection, you got two eyes there. Two eyes. That's the way I like to do it. That's one way you can do it, because there's the subset symbol, the proper subset symbol, that all use that U thing in one position or the other, either like this, like that, or you're going to see it like this in a minute with the union. So let's go down. Now, here's another example, and here's one that we talked a little bit about earlier when we talked about the disjoint sets. We have a set with 2, 4, 6, 8 in it. And we have a set B that's got 3, 5, 7, and 9 in it. And if you'll notice, the difference between those two is A is even numbers and B is odd numbers. So there's not going to be any overlap or common elements in those. So A intersection B is the empty set, open and close. And this is where we start using that empty set symbol, and where it actually kind of means something. Or you use that one. They both mean that there are no common elements, because the intersection of those two sets is empty. All right, so this is the last one we'll look at, and that's the union of two sets. They used to call the United States of America the Union, because the way that the Union works is you have a bunch of states that have the certain amount of autonomy that join together in the United States, the US, the Union. So the Union includes all of the states put together. We could look at it as or if it's in one state or the other state, then it's in the Union. If it's in Texas, or if it's in Delaware, or if it's in Montana, or if it's in New York or Pennsylvania, then it's in the Union. because each one of the individual states are in that union. So now this symbol is the upside down one now from the intersection, and that reads union. Union. And it's the sum total of all of them together. And when you take two sets and put them together, if they have any of the common ones, you don't count them twice. That's kind of the same thing back about the definition of a set. So another way of looking at it is the union means or, the intersection means and. So if we say intersection, it means that it's something's in an intersection. It means it's in both A and B. If it's in the union, it means that it's in one or the other, or it could even be in both. So here's a little set. I'm sorry, a Venn diagram. Set A has 2, 5, and 7 in it. Set B has 1, 2, 5, and 8 in it. So the union of these two, a union, U for union, U for union, is just all of them. 1, 2, 5, 7, and 8. See there? 1, 2, 5, 7, and 8. 1, 2, 5, 7, and 8. Now the intersection here, which we just previously discussed, there's 2 of them, 2 and 5. All right, now there's a formula for this, and this is going to be something that'll repeat itself. We won't see it in chapter 3, but after midterm, we will see it in chapter 10, another form of it having to do with probability. But right now, we're just talking about the number of elements in the set when we're talking about n. So the number of elements in the union of A and B is equal to, and this is the formula, I'm just saying that because this is important, all right? Like I said, it's one of those things that going to be very useful, and it'll also work in probability. All right, so let's work this out. If we want to find the number of elements in the union, now they've already told us there's 5 of them, but you'll notice that there's 3 in A and there's 4 in B, and if you add those up, that ends up being 7. Well, watch what happens. So the number of elements in A is 3, the number of elements in B is 4, and the number of elements in the intersection is 2. So by this formula here, the number of elements in A is 3, plus the number of elements in B, which is 4, minus the number of elements in the intersection. So 7 minus 2 gives us 5. So there's the 5 in the union. Where did those other 2 go? What happened to those other 2? I've been talking too long. I need to get y'all in the game. Well, the 2 that went away are the ones that were the same, because we don't count them twice. Because those 2 in the intersection are both in A and they're in B. Since they're repeated, what the subtraction does, it just takes out the number of repetitions, therefore eliminating the double count. Like I said, that's an important formula, and we'll see it later on as well using it again. And these concepts of and or will repeat themselves throughout the course. That's why we're going over them here, the and the or for the union, for the intersection in the union. All right. So we'll just hit this one more thing. All right. This one is slightly different. A is 2, 4, 6, and 8. So it has 4 elements. Set B also has 4 elements. Well, you know what? They don't have anything in common because A is even, B are odd numbers. So the way we find the number of elements in the union is we add up what's the number in A, which is 4, the number of elements in B, minus the number of elements in the intersection, which is 0. So we don't subtract anything, just 4 plus 4, which is 8. And then you can see if you put these two together, there's no repetitions, there's none to take out. 2, 3, 4. So that's 1, 2, 3, 4, 5, 6, 7, and 8. That's the way this formula works. It lets you know how many, but in order to find out how many are in the element in the union, you've got to know how many is in the intersection. You add up the element, the number of elements in each of them, subtract out however many is in the union. All right, so that's enough for today. You can use the rest of the time if you want to work on. Yeah. In Canvas, I got to put this in here because of the way I got to do this immediately. So inside of quizzes, there's because every class that meets virtually and online, whether it's virtual like us, which is called synchronous because we meet at this one time, or the onlines that are asynchronous, where students work when you got time. They have to have a verification quiz. So this here, you're going to have to, if you've already got Respondus loaded for Canvas, then you're not going to have to worry about this, but you got to download another one. And I tell you what, let me just make sure. And I'm going to put it in the quiz in case you need it. Oh, that's the instructions with that. So anyway, just do this as soon as you can. I think where's the download? There we go. I didn't have download in there. I guess 4 is what we want. So I'll just put this in the quiz. So there you got that. If you need it. But that one will be the same as for any other class where you test on Canvas with Respondus. So anyway, it's not got any, it's not, you don't worry about the questions. You just got to test your respondents. That's all it is. There's a couple of silly questions in there. So do that and upload your photo ID in here. Where's it at? Do I not have it in here? Maybe I didn't put a time on it. Let's see if I can find it. I know it's in here. There we go. That's it right there. I don't know why it puts it way down at the bottom. Maybe if you're a student, it's different. Maybe it's easier to find. Right here. This right here is not yours. So don't worry about that one. But this is what you got. I'll take care of that. So don't worry about that one. This is the one you want. That's from the last semester. And you'll have that too, but I got to recycle it, go in there and change the date to when we get closer to the midterm. All right. If you got any questions, I'm here. I'll see you Monday. Have a good weekend.
I do have one question.
Mm-hmm.
I noticed in one, in the assignment detail, like one, I had a graded, I think it was integers. And it says
Mhm.
submit, but I'm not sure where that came from. I don't know if that was on your side or,
Can you share with me what you're seeing?
I have it on my phone, but yeah, I can.
Can you like, so you can hold it close to the camera or something?
Let me see. And it says it was graded, but I'm not.
Oh, okay. That's from the 020 class, right? That's the first assignment over in Alex. Look,
Okay, because it says July 17th as the due date, and then it says
right. That's what I was about, because that's the last day of class. All the assignments for the path, the homework, what they call the learning path in Alex, those things are there. And I think there's like 18 assignments. So
Mhm.
those are all going to come due on the 17th. Now, you got a grade in there, is what you're telling me, right?
Yeah, it says it was graded.
Yeah. Okay. Let me tell you about this.
Oh,
When you first come into Alex in that 020 course, you took a knowledge check. And the knowledge check is to find out what you already know. So
okay,
if you answered questions related to integers correctly, then it's giving you credit.
gotcha. I was wondering, I didn't know because I was doing it and then it came up. And I was like, I didn't take anything. I didn't do it. I didn't know that it
See,
was,
they're all in here. Like that right there.
yeah.
They're all in here. So all of those are part of your homework thing.
Okay.
Actually, I got to pull them all back down here into learning path, but now all these have the correct date because so no Fridays. And get the Newton work up to date as much as you can. Because that's the stuff that's in Newton is your related to the Math 120, the credit bearing class. But yeah, Alex is a strange animal. It takes you through those and it'll give you credit, but you also got to realize it'll take credit away if you answer a subsequent knowledge check wrong. So it can adjust your grade. So be careful about those knowledge checks because it's based upon mastery. It's not, it's basically, it's a path, you don't get off of it. And they want to make sure that before you progress ahead that you've mastered. So it's very hard to get 100 and everything. So they're not individual assignments, essentially. There's individual grades, but that's the way it works. It's a different system than you might be used to.
Yeah, this is
All
all.
right.
So, but thank you.
Yeah, it is. Okay. It's not, but don't worry. Don't stress about it. All right.
Okay, I'll try
Like I
not.
said, is those little those individual grades like integers. If you're talking about 100% for the whole 10%, which is what that counts for, each one of those little 18 things are like the one we were just looking at. What was it? The integers is probably less than 1/4% of a grade. So it's like I said, is each one of those.
Well, thank you.
There's 18 parts to the 10% is what it amounts to. So like I said, don't get caught up in that path and let it mess with your brain.
Okay. If I have any questions, I'll send you a message or something.
Okay.
Yeah, I appreciate
Sounds
it.
good. Tori or
Thank you.
Chantel, you got something?
No, that's it. Y'all have a
Okay.
good weekend.
Okay. Bye-bye.
No, I just was
Shutting this thing
listening.
down.
Thank you, Mr.
Oh.
Cruz. Have a good weekend.
Okay. You too.
Bye-bye.
Bye-bye.